In today's lesson, we're going to be talking about exponent rules. So here's a list of the exponent rules that we're going to be covering. The first one is the product rule, which says a raised to the x power times a raised to the y power is going to be equal to a raised to the x plus y power. The quotient rule says that a to the x divided by a to the y is equal to a to the x minus y power. The power rule, a to the x raised to the y, is equal to a raised to the x times y power. The power of a product rule says that you can distribute the power into everything that's within a grouping. So a times b to the x is equal to a to the x times b to the x. The power of fraction rule behaves very similarly. You can distribute the power to the numerator and also the denominator. So a divided by b raised to the x power is the same as a to the x divided by b to the x. The zero exponent rule says that anything raised to the zero power is equal to 1. The negative exponent rule says that a raised to the negative x power is equal to 1 over a to the x power. And then the last one is the fractional exponent rule. A raised to the x divided by y power is equal to a to the x underneath the root. So the numerator of the exponent is the power, and the denominator of the exponent is the root. Okay, here's some examples that we're going to take a look at that's going to demonstrate why those exponent rules work. So the first one, if we look, it says 3 squared times 3 to the fourth. Let's take a look at what these exponents actually mean. So 3 squared means that we're multiplying 3 times 3. 3 to the fourth means that we're multiplying 3 by itself 4 times. So if we take a look at this, we see that we're just multiplying 3 6 times. Notice what we did with the exponents. 2 plus 4 gives us the 6. So that demonstrates why when we're multiplying two numbers that have the same base, we add the exponents together. The next example says that we're taking 5 to the 6th power, which is 5 multiplied by itself 6 times. And we're dividing that by 5 to the 4th power. So that's 5 multiplied by itself 4 times. If we notice, 5 divided by 5 makes 1, or they cancel. So if we continue to divide those 5s out, we see that all of the denominators were canceled, and 4 of the numerators were canceled, but we still have 2 5s that we're multiplying together in the numerator. So that's going to be equivalent to 5 squared. Again, notice the exponents. We had 5 to the 6th power divided by 5 to the 4th power. If we subtract those exponents, we see that we get 5 to the 2nd power. So again, that demonstrates why that power rule is what it is. Okay, the next one, we have 3 to the 4th that's being squared. So if I first expand the squared idea, we have 3 to the 4th, and we're multiplying it by itself, 3 to the 4th. Each of those 3 to the 4ths means that we're multiplying 3 by itself 4 times. So there's the first one. And if I multiply and expand that 3 to the 4th out for the second one, we again see that we're just multiplying 3 by itself, this time 8 times. So again, noticing the exponents, we multiply the 4 times the 2 to get the 8th power. Okay, 6 to the 0 power, there is that zero exponent rule that says anything raised to the 0 power is just 1. I'm going to use division to show why this is. So let's say that we have 6 squared and we're dividing it by 6 squared. So we would have 6 times 6 in the numerator, and we would have 6 times 6 in the denominator. We said earlier that we can divide those out. So 6 divided by 6 cancels, or would just give me 1. And again, 6 divided by 6 is going to cancel or just give me 1. So we see if we subtract those two exponents, 2 minus 2, we would get 6 to the 0 power. But expanding that out, we can see why that is. That means that both values here divided each other out. So we just get 1. Okay, the next one, we have 2 to the 4th power. That would be 2 multiplied by itself 4 times. And we're dividing that by 2 to the 7th. I need one more there. There we go. All right, again, we're going to divide out those 2's. We see that all of the numerators divide out, but we have 3 2's left in the denominator. So that would be 1 over 2 to the 3rd. If we see what happens when we subtract those exponents, because again, our division rule says that we subtract the exponents, we have 4 minus 7. So if we subtract them, we get 2 to the negative 3rd power. This demonstrates why those negative exponents need to be moved to the bottom, because we had less 2's in the numerator than we did in the denominator. Okay, the last example has 4 raised to the 3/2 power. Remember that the numerator is the power and the denominator is the root. Now, we don't usually write the 2 on the square root, so that's the same as 4 to the 3rd underneath square root. So the square root of 4 to the 3rd power, 4 times 4 is 16, 16 times 4 is 64, and we can square root 64, so that would just give me 8. So again, when we have fractional exponents, the numerator is the power and the denominator is the root. Okay, let's apply some of those rules to algebraic expressions. So here we have x to the negative 2nd power times x to the negative 3rd power inside the parentheses, and that's being raised to the 4th power. Let's go ahead and simplify what's inside the parentheses first. So we know when we multiply same base exponents, we are going to add those exponents together. So this would be x raised to the negative 2nd plus negative 3rd. So that would give me negative 5 as the power, and that's being raised to the 4th. So now we have a power to a power, so we're going to multiply those. So I get x to the negative 20th. We can apply the negative exponent rule here that says that that x to the 20th is going to actually go to the denominator. So we're going to reciprocate that to make it a positive exponent. Okay, so this would be my simplified form. Taking a look at number 2, we have 5 times x to the 4th raised to the 3rd times 2x to the 4th. Okay, so the first thing I'm going to simplify is this power to a power. So x to the 4th raised to the 3rd, I would multiply those exponents together. So we'd have 5 times x to the 12th power. And again, we're multiplying that times 2 times x to the 4th. I'm just going to rearrange these terms because multiplication is commutative. So I'm going to pull the plain numbers out front, so 5 times 2, and the variables to the back. When we're multiplying same base exponents, we add the exponents together, so that x to the 12th times x to the 4th is going to give me x to the 16th power. And we see the 5 times 2 is 10. So that's my simplified form of that algebraic expression. Okay, the next one, similar process is what we just did. It's just a little bit more involved. So in the numerator, we have 2 times 12. That's going to give me 24. This x in the numerator, there's no other x's, so I'm just going to pull it to the side. And we have y to the third times y to the third. I would add those exponents together and get y to the sixth. Let's simplify that denominator if we can. Oh, and we have 3x to the second, y to the fourth. Okay, so let's go ahead and divide. We have 24 divided by 3. That gives me 8. Remember, if a variable does not have an exponent, it really means an exponent of 1. So x to the first divided by x squared, we would subtract those two exponents. So 1 minus 2 is going to give me x to the negative first power. And then y to the sixth divided by y to the fourth, we would again subtract those two exponents, 6 minus 4, and get y squared. We would just want to clean up that negative exponent. So remember, when we have a negative exponent, it reciprocates to make it a positive exponent. So we have 8y squared as the numerator, and that x to the first is going to the denominator. I'm not going to write that first power because, again, it's assumed when there's no power that the power is 1. Okay, the next example, we have a product being raised to a power. So I could distribute that power to each item inside those parentheses. So again, I'm just going to write the first power on the 2 so I don't forget about it. So if I distribute that negative third power to all of those exponents, 1 times negative 3 would give me negative 3. 0 times negative 3 is going to be 0. And 2 times negative 3 is going to be negative 6. I'm multiplying that times 2 times y to the first times x to the third. And I'm also going to write that 1 exponent on the 2. Notice we have same bases here. So again, since we're multiplying those same base values, we could add their exponents together. So I would have 2 to the negative second power, negative 3 plus 1. Here I have x to the 0 power times x to the third power. Again, I would add those exponents. So 0 plus 3 is 3. And then y, we have negative 6 plus 1, and that's going to give me y to the negative fifth power. Again, cleaning up those exponents, those negative exponents. The x to the third is positive, so I don't need to move that. But the 2 to the negative second, to make it a positive exponent, I would put it in the denominator. And y to the negative fifth, to make that positive, again, I would put that in the denominator. Now, we could actually do 2 squared. So I'm going to simplify this one more time. X to the third, 2 squared is 4, y to the fifth. So final answer, x to the third divided by 4 times y to the fifth. Okay, that last example, we can't really see it. It says, there we go, x to the 1/2 times x to the 7/8. Again, since we're multiplying those two, I would have to add the exponents together. Be careful because when you add fractions, we need a common denominator. So our denominator would be 8. So I'm going to change this 1/2 to 4/8. So now we would add those exponents together. So x to the 7 plus 4 would give me 11/8 power. That means that it would be x to the 11th power, the 8th root of that number. So the 8th root of x to the 11th. Again, remember that numerator is the power and the denominator is the root. Okay, we're just going to look at a few more examples together. So this example, we have a product that's being raised to the power. So again, I would distribute that power to everything inside by multiplying. So 2 is going to be raised to the 1 times 3, or just third power. X is going to be raised to the 3 times 3, or 9th power. And Z is going to be raised to the 2 times 3, or 6th power. In the denominator, we have x to the third times x to the negative fourth. So I could add those powers together to get x to the negative first. The y, I'm just going to pull across y to the fourth. And then the z's, let's also add those powers. So we have z squared times z to the third, which would give me z to the fifth. Okay, so notice now I'm dividing x to the ninth divided by x to the negative 1. So I would subtract those powers. Now, be careful there, because 2 to the third, I'm just going to pull that over. X to the ninth divided by x to the negative first, we would subtract those powers. 9 minus a negative 1, we'd actually add. So x to the 10th minus a negative makes plus. The z's, we have z to the 6th divided by z to the 5th. I would subtract those powers, and I would get z to the first. Notice I haven't done anything to the y's, so that y to the fourth is just still going to be in the denominator. There's one more simplification that we could do. 2 to the third power. 2 times 2 is 4. 4 times 2 is 8. X to the 10th z. I don't really need to write that first power on the z. And it's being divided by y to the fourth. That would be my simplified version. Okay, our next example, we have 2p m to the negative first q to the 0 that's being raised to the negative fourth. Again, I'm going to put those imaginary 1 powers on both the p and the 2. If we distribute that negative fourth power through, we'd have 2 to the negative fourth, p to the negative fourth, m to the positive fourth, negative 1 times negative 4, and then q raised to the 0 times negative 4 would be the 0 power. We're multiplying that times 2m to the negative first, p to the third. And we're dividing that by 2 pq squared. Now that numerator has multiple m's, multiple p's, so let's go ahead and add those exponents together since we're multiplying. Oh, and I'm also going to write the exponent of 1 on that too. So the first item, the 2, is being raised to the negative fourth power, and then times 2 to the first. Again, we would add those exponents. We have 2 to the negative third power. The p's, p to the negative fourth times p to the third. Again, I would add those powers and get p to the negative first. The m's, we have m to the fourth times m to the negative first. Again, I would add those powers and get m to the third. Q to the 0 power. I could just write that as 1, but notice there is a q squared in the denominator, so I'm going to leave it. Q to the 0. Okay, I'm just copying that denominator back underneath there. Okay, since we're dividing, again, we subtract exponents when we divide. So we have 2 to the negative third divided by 2 to the first. We would subtract those exponents and get 2 to the negative fourth, negative 3 minus 1. The next variable, we have p to the negative first divided by p to the first. Again, we would subtract those exponents. So negative 1 minus 1 is going to give me p to the negative second power. There is no m to simplify that m to the third with, so I'm just going to pull that down. And then we have q to the 0 power divided by q squared. Again, we would subtract those exponents. So 0 minus 2 gives me q to the negative second power. Now, that has a whole bunch of negative powers that we need to use that negative exponent rule on. So remember, we reciprocate to make the power positive. So I'm going to leave the m to the third in the numerator because it is not a negative exponent. But everything else is moving to the denominator. So 2 to the fourth, p squared, and q squared. Last step to simplify, I could simplify the 2 to the fourth power. So 2 times 2 is 4, 4 times 2 is 8, and 8 times 2 is 16. So final answer, we have m to the third over 16 p squared q squared. And that would be the most simplified version of that expression. Okay, our next slide is the U-try. So take a look at that, see if you can simplify it. Pause the video here, and then when you're ready, unpause the video to reveal the answer. Okay, this example, we get j squared over 8h to the 7th k squared. I first distributed the negative 2 power to everything that was inside using that power of a product rule. I got 2 to the negative second, h to the negative second, j to the negative fourth, k to the fourth, h to the negative eighth, j to the second, k to the negative 8. Kept that denominator pretty much the same, just pulled it over, and I added that exponent of 1 on the 2. So then I first subtracted the exponents on the 2's. So negative 2 minus 1 gave me negative 3. I added these h exponents together that were on the numerator. So h to the negative second times h to the negative 8th gave me h to the negative 10th. But then we were subtracting a negative 3, or negative 10 plus 3. That gave me that negative 7 power on the h. J's, same thing, negative 4 plus 2. That gave me negative 2. And then we were subtracting a negative 4. So negative 2 plus 4 gave me a positive 2 power on the j. The k's, we had 4 plus negative 8. That gives me negative 4. But then we're subtracting a negative 2, or adding 2. So negative 4 plus 2 gives me k to the negative second power. And then simplifying and cleaning that up a bit, j squared is the only thing that has a positive power, so it stayed in the numerator. Everything else moved to the denominator. 2 to the third became 8. H to the negative 7th became h to the 7th in the denominator. And k to the negative second became k squared in the denominator. So final answer, j squared over 8 h to the 7th k squared. This concludes the lesson on exponent rules.